All right, so here we are with this balancer in all of its glory. This is a dual plane balancer with using these 50 kilogram load cells. There's a magnetic rotary angle position sensor. It uses a small magnet to sense the position. Using a teensy microcontroller here for all of the data acquisition from the two load cells and the position sensor. We've got just like a 350 watt DC motor for driving the crankshaft. It's running through a series of bearings to the main pulley. You've got a little spring loaded here. Got this rule-on thrust bushing here that basically controls the axial position. And there are these four primary rollers here. The rollers are made out of PEEK, polyether ether ketone, and they are supported by these dual race ball bearings, which actually are the ball bearings for the timing belt and the Nissan VG. Written this Windows interface here, which shows we got two bullseyes for the front load cell, the rear load cell, and then we have a graph here for the waveform. I'll go ahead and spin this thing up. First thing we do is do a calibrate for the force. Basically, it zeroes out the load cells, and then we can go to a stream here and actually see our rotation. Double check that our sensors are zeroing out. You can see as I'm pushing on this guy, it's even the lightest touch creates a signal here. And this is just the stream mode, which is in real time. But for running this thing at speed, we can't be streaming data through the serial port. It just uses too many clock cycles. So we do a burst mode. So what I'll do first is go ahead and get this thing spun up to speed. That's just about slipping. We get this guy up to revs, and we will do a burst mode. So basically it takes from 150 samples and then it plots it out, shows you vector and amplitude of where the heavy spot is. This thing is actually really well balanced. This is spinning at 1100 RPM, and you can see actually here there's double heavy spots within a 180 degree rotation, which is impossible to have. What you're actually seeing here is the natural resonance of the support for the bearing pedestals. So I'm gonna stop that there. But yeah, so this is considered a hard bearing balancer. The bearing supports are actually supported by these thin spring steel plates, which is actually from a bandsaw blade. Most of the rigidity actually comes from the sensor itself, and the natural resonance of these bearing supports is at about 35 hertz, and we're spinning this thing up to 1000 RPM or so, which puts us at about 17 hertz, at least cycle time for one rotation. And at that point, you start getting into these harmonic excitations. But I took this crank up to my local machine shop and spun it up, and even with this Frankenstein homebrew, I was 1.08 grams on the front end and 1.67 grams on the rear end. So lots of ways to improve the accuracy of this, namely either going with angular contact ball bearings rather than 60,000 plus mile expired timing belt bearings out of the used parts bin, or going to like Teflon pad bushings instead. So there's that.